take the C0 and on the left hand side you add 2 Hadamard's. Okay, right? So basically what I'm trying to do is I'm trying to create a plus state here and a plus state in the bottom. Okay, a plus state at the first qubit, a plus state and the second qubit. That is what I'm doing. Or if you want to create a minus state in the bottom, you just simply add a X gate, okay, before here. We'll see that also, right? Okay, so the input for the C0, if you see, is a 2 pluses, 1 plus, another plus. If you want to write that explicitly in computational basis, 0 and 1 is a computational basis. You want to write, you write as 0 0 plus 0 1 plus 1 0 plus 1 1. In fact, it is equiprobable 2 qubit system. Okay, right? So here when I do the C0 gate carefully, if you see, what C0 does is, if the control is 1, target has to be flipped. So here in the 4 cases, first 2 control is 0, so nothing happens. But in the third and fourth, if you see, control is 0, so target flips. But the thing here in this case, control even though high, target even though it is flipped, I don't see any effect. You know why? Because even though probability amplitudes are shifted, both being positive, I'm not seeing any effect. Okay, so swapping is happening, probability swap, amplitude swapping is happening, but no effect. So that's why now information is flowed from top to bottom, but I'm not seeing. So let's add a X gate here. Okay, right? Okay, come down. Okay, this see effect. This is input, and there is output, and you plot the input and output. Okay, and there are 2 qubits. What is the where they are pointing out? That is what actually it is plotted on a block sphere. So that is what you see in this notebook. You just ignore those things. Now let take this scenario. Okay, so let's say the C0 gate is here at this point. Now what kind of an input is going into the C0 gate? Okay, right? So voice is not fine. Okay, let me see why voice is not fine. Okay, I have muted here, so I don't think so any problem in the voice. Yeah, now I want to see into the C0 what kind of inputs are going here into the C0. Same kind of inputs are going. Okay, here same kind of inputs are going. Some output I am getting. That output I am not able to recognize the effect of C0 there, because the input, whatever input going into that, both are same. That's why I'm not seeing any effect. Okay, so as if plus plus here, plus plus here coming out. Okay, now to see the effect, what do I do is I create or I add a X gate in the second qubit, so that now what happens? The top I have a plus gate, bottom I have a minus gate. Remember, now it is a Qiskit Jupyter notebook. Earlier I used to write Q0 first, Q1 later. For us, usually we write left to right. Okay, now we are writing right to left as per the Qiskit. In the Qiskit, Q0 is in the plus state, that is on the right. Q1 is in the minus state, which is on the left. Okay, now a C0 gate is here. What is going into the C0 gate? If I write explicitly, this is what going into the C0 gate. Okay, a minus multiplied by plus gives me this kind of a thing. Okay, we have seen this while deriving. Okay, now you see, let's add a C0 gate Okay, before adding a C0 gate, you can plot this qubit 1, qubit 2. Okay, qubit 1 is in the x direction, okay, plus direction. Qubit 2 in the minus direction. You see, okay, x is equally probable, minus x is also equally probable, but there is a relative phase. That is what showed here in the block sphere representation for these two qubits. Okay, right? Fine. Now act a C0 gate. Now act a C0 gate. Now you see, interestingly, the moment you add a C0 gate, information should flow from the top to bottom. On the top we have a plus, on the bottom we have a minus. Okay, what should we see? Information should flow top to bottom. Okay, let's see the effect of C0 gate here. Because of right hand side is a high, left hand side should, okay, what is this? Minus and plus, minus and plus, yeah, okay, plus minus, plus minus. Okay, now you act a C0 gate on this. Right hand side is a control, left is a target. Okay, so only changes would happen in the second term and the third term. So second term becomes 1 1, third term becomes 1 0. That is what happening here. Second term becomes, okay, second term becomes 1 0. Last term becomes 1 1. Wait, okay, they have already interchanged. Yeah, 1 0 and 1 1. Okay, so this becomes 1 1, this becomes 1 0. So there is a minus sign. They put this here and they put this one here. This minus will come at the second term. Okay, a positive term comes at the right. The third term remains as it is. You see, third term remains as it is. Okay, so it is already done in this equation so that they can figure it out what is this output correspond to in terms of plus and minus basis. In terms of plus and minus basis, if you see, this is minus minus. Okay, this is minus get minus get. Now what is happening? Okay, instead of plus inducing plus in the bottom, minus induced this nature on the plus in a reverse fashion. So that is what happening here. Instead of information flowing from right to left as per the cascade, information is flowing from left to right the moment you add two Hadamards on the left. Okay, now if you add two more Hadamards on the right, you would see, okay, you would see like C0 completely becoming reverse. C0 is there like this top to bottom. The moment you add Hadamard, it becomes a completely reverse. Okay, right? So that is what is showed here. Okay, right? So you can cross check the results. Okay, let me do some. In fact, we can run the codes here. Okay, let me do. Okay, so this is a gate. Display, where is the output? Is there output? Yeah, here it is. Okay, so they're plotting the output. So let me do, right, the input. Maybe we need to run from the top. Okay, let me run all the cells. Okay, shift, okay, run this particular cell. Okay, it ran, and then I will run the second one. So I'm plotting a conventional one. Okay, so this is 0 zeros. I'll get plus plus. Okay, right. Again, let me run this one. Okay, again the same. Let me plot it. Okay, so let me plot the block sphere. Yeah, I have plotted a both are in plus plus. Okay, both are in plus plus. plus plus going, what kind of a circuit that is? This is a circuit. Okay, now I add a minus. The moment plus, like a plus and minus, for that I use a x. So this one. Okay, now same thing, you can create a plot for that. Okay, I plotted. The first one is plus, second one is minus. Okay, add a C naught, run. A C naught is run. Okay, plot the result. Okay, see, both become negative, negative. Okay, right? And here, okay, so you can also do one thing. You can create, right? This is a gain. Okay, right, for this, okay, for this kind of a thing, what is the matrix, coming up matrix? Coming up matrix is a C naught gate matrix. You see, the first quadrant is identity, the last quadrant is X gate. That is what initial C naught gate. Now the moment you just remove this H, okay, right, you remove the H and reverse it. Okay, you just draw the same. Okay, you will get the same. You, instead of that reversing, let me reverse the C naught. Okay, and if you plot for both situations, okay, you get see, you get a different C naught. Okay, earlier C naught is different, this C naught is different. But the moment I add Hadamard's, I would get this kind of a equality. Okay, it's basically becoming a reverse. Adding Hadamard's, it becomes a reverse. Okay, so in this way, you can just induce a phase shift or a phase going in opposite direction. Okay, right? Now you can do anything else. Let's say the control phase gate is there, information flowing from top to bottom. So let's say this is top to bottom controlled phase gate. You can enclose within the Hadamard, and within the Hadamard you can enclose, and you can create a reverse information flow. Okay, right? This is a phase kickback for you. Now let's go for Bernstein's Vajrani algorithm. You can watch the video, right? So watch the video. Okay. Now, so maybe I'll just what exactly here? Maybe I'll just use my hand notes and explain, and then we'll come back for this thing. Okay. So let me stop sharing here. Yeah. Yes. Okay. Start sharing my hand notes. Okay, let me take a new notes. Yeah. Right. So now I have a S. I have some S. Okay, I'll write in the form of vector, or I can say in the form of something. It can, let's say 2-qubit system, n equal to 2. For n equal to 2, let's say S has no effect, means no flip. Okay, if S is like this, okay, let's say first bit flips. Okay, that is another way of effect. This one, second bit flips. I'm writing the errors in the system. Okay. And if this is there, both bit flips. Okay. So errors in the system. Represented by some S state, or not a state, some S hidden bit flip string. Yes, hidden bit flip string. Okay, right? So this is a system has a problem. I want to find what is this S would look like. Okay, if I write this in terms of quantum states, it would be 0 0 0 1 1 0 1 1. Okay, right? Now whether it is existing in 0 0 form or 0 1 form, I want to find out. Okay, right? I have to query that. What was the query earlier? I was adding. Okay, I have a note somewhere here. Yes. Okay, I was adding 1000, multiplying, and see whether I am getting 1 or not. If I have 011, I'm getting something. Classically, I am doing 4 queries. From the 4 queries, I'll figure out what is the S would look like. Okay, this is a 4 qubit system, but I want to do it for time being 2 qubit system so that I will understand. Okay, 2 qubit system, right? S1 is like this, S2 is like this. Among the S1, S2, where 0, this is S1, S2. Okay. Now what I will do a Hadamard acting on that location. Okay. It is like there are 2 places on the chip. There is a trouble or there is a issue. So on that locations, I will shine a stream of laser photons, and those photons go and hit those locations and produce some output. Okay, right? So that is simple experimental view for us to understand this Bernstein's Vajrani algorithm. Mathematically, what I was showing on the paper is equivalent to shining 2 Hadamard photons or pi by 2 pulse photons onto the location where there is a error is creating. Okay, right? So let me do Hadamard acting on S1 tensor, Hadamard acting on S2. In short, I will write it as Hadamard square 0 0 in the first case. No effect case. No effect case, what I will get, as we guys all know, it would be equally super probable situation 1 0. This is equally probable. Okay, if you want, if you usually follow the same analogy like 0 0 0 1 1 0 1 1, let me do that only. Okay, so usually people prefer that 0 1 1 0 1 1. Okay, now in the second case, let's say error is occurring only at the second qubit. So there I'll have what I'll have is, okay, so 0 0. You can cross check. The output I get is 0 1, okay, plus 1 0 1 1. If you want, I can cross check for you. Okay, what is this is 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2, which is equal to 0 0 plus 1 0 1 plus 1 0 minus 1 1. Okay, right? Am I right or wrong? Wait a minute. 0 0 0 1 plus minus. Okay. 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 Let's 0 0 0. Okay, this is a minus. That's mistake. Correct. This is a minus sign. Okay. So that is what we got. Now, what is Hadamard acting on? 1 1. What I mean is, let's say there are two locations where I shined the photons. In fact, there is a problem there. Both locations are flipping the information going through that location. The gates are problematic. They're supposed to keep quiet. They're actually flipping. They're acting like a X gate, bit flip. So what I will have here is, okay, so again, you can cross check, better cross check every time. 0 0 0 minus, okay, this would be minus, and the last one is plus divided by square. Okay, so 0 0 minus 0 1 minus 1 0 plus 1 1 divided by square root of 2. Okay, right? We got that. And H acting, maybe we should have done it before, 1 0, which comes out to be, okay, which comes out to be 1 by 2. Let me write down straight away. 0 0 minus 0 1 minus 1 0 plus 1 1. You can remember simple technique. What is the technique is, whenever you have two zeros, you put all positives. Whenever you have 0 1, you put middle one plus everything else minus. Okay, minus minus. Whenever I have 1 0, you put the left two minus, the right one is plus. When you have both 1, okay, right? Okay, wait a minute, there is a mistake for 1 0. For 1 0, I have plus minus minus. Yeah. You can come up with your own way of remembering, or if you don't remember, you please derive. That's not going to consume a lot of time for you. Okay, so first thing is I added a Hadamard on that. Okay, so then I will try to do some kind of a function. What is the function is, which is equal to s into x modulo 2. Okay, right? Right. So, by the way, as we all know, okay, H acting on, right, s vector is equal to, in this case, square root of 2 square. If you recall back, summation, okay, z belongs to, okay, right, z belongs to 0 comma 1 tensor square minus 1 to the power of z into s z kit. You guys know that. Okay, right? So using this, right, now I can go a simplification or generalization for any s, for any s 2 to the power of n, z belongs to 0 comma 1 n minus 1 to the power of z into s c. Okay, now I have to run a query. What is that query is, whether the output is 0 or 1, because I'm doing a modulo, the modulo symbol. Okay, so let's say at this point, let's say I have a quantum state psi. Okay, right? or we have, let's say, quantum state X. Okay, right? What is this quantum state X is? Or if you are comfortable in only dealing with S, let's call it as a S. What is that quantum state S? Okay, S is going, right? So there is a S here. I want to know what is that S would look like. What I will do, take that, act some unitary function, okay, and whatever a unitary function is, I'll take a hand unitary some ancilla, add to that. Okay, right? Now whenever S is there, a unitary gate is acted on the S, what we will get? Minus 1 to the power of, okay, right, minus 1 to the power of if I have unitary function f is depending on some x, so I'll have minus into x. Yes, get, this is what we will have. Okay, so we derived this yesterday. Okay, now what I will do, let's say I act again, whatever is coming out here, I will act 2 Hadamard's. So what did I do? I started with the Hadamard's, ended with the Hadamard's, and left the C0 gate, like controlled C0 gate as it is. I enclosed with Hadamard gate. What happens now is the information flows upwards. Okay, so the information flows up. Because of this, what happens? Okay, whatever is the output you are getting at this point, whatever output you are getting at this point, let's say get back to here, there is a diagram, yeah, here. So if you start with all zeros, okay, and if you enclose some unitary function, basically what I am trying to find, I am trying to find what is the effect of internal system. And the internal systems, to find the effect, first I added Hadamard, then a unitary function followed by another Hadamard. The moment you do, what is happening, you would get S exactly out. Okay, so that is what I am saying. I am saying the moment you act a system of Hadamards at this point, you would get S out as this. So this is, okay, so this is maybe all zeros, or you can say this is maybe yes. Okay, so I'll just show you algorithm, how it is implemented. Okay, let me exit the sharing here and share in my okay, yeah. So this is Bernstein's Vajrani algorithm, right? Let's say my S is like 6-bit system. Okay, what it's saying is, okay, we have to count from right to left now. First qubit, second qubit, third qubit are going to be flipped. Okay, fourth, fifth, and sixth are also going to be flipped. In this case, what should I do? Okay, first I have to find what is the length of my bit string. Okay, so length of my bit string, right? I am finding. Okay, I will start a quantum circuit which is having a query register having n bits and one ancilla bit. That's why I'm creating a quantum circuit of n plus 1 registers, and I need to have a classical register to store the information. I'll have n classical registers. Okay, right, now If you want, you can run the code. Okay, right? I'm running the code. I'm creating a circuit. Right now, okay, for simplicity, maybe let me comment this comment. Let's start me with the 0 1. Okay. Okay, so I have to put the inverted commas. Yeah. Okay. Now the bit string is just length of 2. So the circuit would be, okay, let me plot the circuit and then we will come back what is consisted. Okay, wait a minute. Yeah, it's a 2 bits, 1 answer bit. Okay, right? Now, usually what I'll have, there is a C naught happening. Okay, maybe you can just say only 1. Okay, so this is why you will easily understand. Okay, let's plot. Yeah. So let's say S is just a single bit. It is going to flip. I want to know that is S is 1. I want to know that. So I will take S as it is. And from the S, I will run the information going backward with a C naught. But my ancilla bit is there. Na? So I enclose with Hadamard so that the information goes in the reverse way. Okay. If you do that, and if you do and make a measurement at this point, you are not making a measurement here. If you make a measurement at this point, okay, you would get exactly 1. Okay, so there is 2 possibilities for S can be 0 and 1. So S is coming out to be 1 with how much probability? 100% probability, with 100% count. If you are performing the experiment, let's say how many times, I think somewhere they specify number of shots. Okay, I think it's not there, but for certain number of shots it is going to shots is 1 here, only 1 shot. So you can increase, let's say 100 shots. Okay, for 100 out of 100, this is running on a simulator. See, Qasim simulator. That's why you're getting 100% result. If you run it on a Qasim simulator, okay, let's say this one. Okay, this one is also 100. You can run in on real hardware by logging into the system. Then I think you will get, you will not get 1000 out of 1000 the same result. You would get 900. Maybe some errors are there. Okay. Now let's get back S being a flip like 1 0. Okay. Right. Now let me give S. Okay. Specify the circuit. Plot the circuit. Okay, circuit is plotted, right? Fine, I think plot, yeah, circuit is plotted, 2 S and 1 ancilla, right? Now you see, interestingly, whenever S is 0, I'll not have a C naught running from that bit to the ancilla bit. So S I have taken 0 1 na? 0 1. So only for 1 it is running. Okay. Now I enclose everything with Hadamarts, then run it. You should get 0 1. See, 0 1 you are getting. If you run it for several shots, you will get 0 1. Okay, right? This is 100, this is 1000 shots. You can keep going a game like this. Now let's say 10111, 5-bit system. Errors, 5-bit errors. Okay, let me draw the circuit for you and plot the circuit. You see 5 bits for S, 1 ancilla. Wherever there is a 1, I run a C naught from there. There is 0 here, correspond to Q3, means the 4th bit. That is what I have chosen. See, 4th bit from the right you have to count. 4th bit is 0, so C naught is not coming there. Okay, So that is what your UF unitary function is, many C naughts. Okay. Now you run the count, measure, make the measurement, and run the count. Okay. Fine. So the moment you run the count, you see you are getting the output 11101. Okay. So this is how the nature of the errors in the system could be easily determined using this kind of a circuit. Okay, right? So in fact, this circuit not only taking one particular scenario into picture, it is taking all the cases. Like S can be all zeros, S can be all ones, S can be 00111, S can be 11011. So it runs on all the cases. What is the correct probability? What is the actual scenario? That is actually going to come with the highest probability. That is we are getting as an output. So this is a Bernstein's-Fojrani algorithm for you. Okay. If you want to run this on a classical algorithm, okay, so I have it for you. Let me show you. So this is a technique. So how many queries? For example, 4-bit system, you would be needing 4 iterations or 4 queries. If you have 5-qubit system, you need to have 5 queries, because basically you are trying to solve algebraic equations of certain unknowns, right, simultaneously. Okay, right? So without having equal number of equations, you can't solve the algebraic equations. Let's say 3 unknowns are there, you strictly need 3 algebraic equations. Similarly here, if I just take a 4-bit string or a 4-bit hidden string, yes is there. Here in this case they are writing as a, yes and a both are same. If 4-bit is there, you have to use 4 queries, because you are trying to find whether the first one is 1 or the second one is 1 or the third one is 1. Third one is not 1, you are getting 0. If the third one is 1, you will get 1. So you're just taking either product or you are trying to add and see the output. Okay, right? So this is a classical and a quantum. Okay, again this is a, so somewhere some books they show I stands for identity, not having anything, or you can put identity just for your convenience. People write the codes in that way. Okay, right? Okay, so yeah, I think somebody was asking me run the Bernstein's-Fojrani algorithm on IBM. So on the IBM, you have to come up with a composer and do that. Okay, let me run it on Q Universe quickly. Right. Okay, I hope my, okay. So it is taking time. Let me, okay, let me run on another system. Start sharing. So I encourage everyone to please go and create your Q Universe account, log in. Okay, log in. This is more handy for the very initial stage. This is the best one as of now compared to IBM. IBM is too good, but to learn, this is the best. Okay, right? It will take some time. So like you can play around with adding the gates. I showed you on the second day, I think. So otherwise I want to feed now. You click on the algorithms. Okay, let's say I want to add a Dutch algorithm. Okay, so what kind of a function you want to add, that you can choose. Okay, right, you want to add, so if you want to add a load Dutch Joyce algorithm. Okay, so okay, this is hanging. Yeah. So it is not loading, I think stucking. Okay, let's go for Bunsen-Vajrani algorithm. Okay, so enter the secret key. Let's say I entered all S is equal to all fours. For that, load the circuit. Okay, I have to choose four. Okay, you have to choose 4 qubits. I think it's a 4 or 5. Yeah, 4 qubits and 1 ancilla. Right, this is a corresponding circuit. It by default it locks. Okay, and it runs also. You see the result. Okay, ignore the last one. Right, so you'll have 1 1 1 1 1 1. Last one correspond to ancilla. You see, right? So I'm not doing anything there. It gives as it is 0. Okay, now let's get back, go back. All right, or you can change here itself. Here also you can change Qiskit. So Qiskit code is there. Shorts. Right. I think there should be somewhere I can change the input. Manage is number of qubits. Quantum registers is 4. No, you can't do that. Okay, let's go back. Algorithm. Okay, my secret key is 1011. Not a secret key. I would say error occurring in the circuit is 1011. You can say in that way, or also you can say a secret key. Let's say I want to have 1011 to be detected. Again, I have to choose 4. Load. For that, I will have, see, 0 1 0 1 1. That was my code in the first place. Okay, right? So you can feed any algorithm you want. You see, Simon algorithm is there, and even this okay, superdense coding is there, quantum Fourier transform is there. Okay, so you can start with a Dutch algorithm if you want. So Dutch algorithm is what? Finding all the functional values at a time. Okay, so this is going to give you that. Fine. So 0010 value you find. Okay, go back. Algorithms. Okay, so load Dutch Joyce algorithm, finding functions and their sums. Okay, so likewise, you can feed the circuit by default and you can run. Okay, right? So this is algorithms for you. Okay, so let me conclude. There is a plenty of materials. Okay, this is a phase kickback. Phase kickback is the one which is very important for case of Vajrani algorithm. What basically we are trying to do is we are trying to ensure that information flows in a reverse fashion. Okay, C0, I want to reverse it. So for that, what I do? I add Hadamard. Once I do that, okay, where is the phase kickback? Yeah, this is a phase kickback. Okay, wait a minute. Yeah. Bunsen-Vajrani algorithm. Okay. Right. And you can easily find what is that internal error in the system. Yes. Okay. Right. So I'll stop here. If there is any questions, I will take. Okay, there is a question. Quantum computing book name for beginners. After unitary function acting on S. Right, sir. Yeah. Yeah, these slides are available on IBM. Not a slides, they'll say documentation. These things used to be on the IBM experience itself. Now they have removed it, they have made it to GitHub. You search, you would get all the episodes. Like you can just find Bunsen-Vajrani algorithm. You can find a Dutch algorithm. Everything is there here. Okay, see here. You can just copy and paste and then run the codes. Okay, the book somebody was asking. The book name is Nielsen and Chuang. Nielsen and Chuang. Why one is called an ancilla bit? As it fixed star, we can take it 0. You can take anything. Yeah, ancilla is your choice. You can take whatever you want. Okay, it is being used to just to know. Let's say it's like a readout ion, readout atom, something like that. If some information is there, I want to read, I would send something near to that, and this will extract the information from there, and it doesn't disturb this. It keeps as it is. So that is like that. Ancilla is like that. Factoring of primes using Shor's algorithm. Yeah, I think the Shor's algorithm is going to be discussed. I think, let me see when it is going to be discussed. It's there. Okay, HHL algorithm is there. That I am going to talk about. Okay, prime factoring, I think Mustafizur will show you. Okay, right? You people can even check yourself, right? Simon's algorithm, Grover's algorithm is here. Where is the Shor? Wait a minute. Here it is. Enter the number. Let's say I want to factor 15. Load the circuit. So circuit generates only with the Qasim code. Okay, I have to choose that, huh? Cascade Qasim, open Qasim. Okay. Okay, now I have to get back. Algorithms. 15. Load. Okay, not a binary. Okay, I have to convert that 15 into binary numbers. Okay, 15 means at least I need 3 qubits means 8, 4 qubits means 16. 4 qubits I need. Okay, what is the 16 is written like? Okay, 16 is 1 0 0 0 5 zeros. Okay, let me load this. 4 zeros. Yeah, this is is it running? Only circuits with fewer than 6 qubits can utilize the probability simulation. Okay, that has an issue here. Maybe let's do 6. Maybe let's do 6. Okay, maybe 1. Okay, 3. Let's do it. 3. Load. Yeah. Okay, so what I'm getting result? All are equal probable. I think I'm not finding the 2 into 3 is 6, right? Okay, primes we have to take. 6 is not a co-prime. Oh, that is also there. 3 into 5, 15 is the one. I think this show. Okay, I'm trying in the Simon's algorithm. Okay, let me try here. 15. Okay. Okay, we have to see. I think this one I have not used much. So you can figure it out. I think he will tell you. I think Mustafizur would introduce to you people the details. Okay. Okay, can we run QSVM here? I am not sure, but like this one is as of now is kind of a limited. Okay, we need to see, choose the file. Okay, input file, data file you can feed and see how good it is. It is just in a trial stage, but if you use, there are codes, Qiskit codes available for QSVM, and then you can run then either on Google Colab or install Qiskit on your system, and you can run on your system. Yeah, it is possible. Okay, so to the start, Just to understand, I think this set of algorithms are very, very handy. This Q universe. Okay, right? Okay, so a real scenario, any labs are available in India to get quantum programs are executed and get results, sir. Yeah, there are labs, but they don't allow outsiders like that. They only use for research related. Day-10 is there, some 2 to 3 qubit or up to 6 qubit, I think. ISC also has. Okay. Which algorithm is the best for random number generator? Okay. See, every classical algorithm is actually random number generator is going to generate a pseudo random numbers based on some equations with some period. Okay. But when you choose a random number from, take a superposition, make a measurement, we don't know where the measurement is going to fall. So that is how quantum random numbers are going to be generated. So there is a separate algorithms for that. So that would be a best random number generator, quantum random number generator. Okay, which algo is best for medical images? So medical image processing, I think people are starting with this VQE and then HHL and QAOA. This algorithm. Basically, you take a data, you are trying to find a minimum energy or minimum some minimum of that particular data. So they are going to convert that data into Hamiltonian, and they are going to find energy eigenvalues of the Hamiltonian. The lowest eigenvalue would give some information about the system. Okay, so that is a VQE for you. I think we'll touch that in my next session. How far it is to correct perceive the quantum algorithms are being executed in classical computers? Right now, correct. Your statement is absolutely right. Yeah. So you are trying to run classical algorithms, sorry, quantum algorithms on the simulators which are realized on a classical computers. Okay, the qubit which we are saying, it is actually realized on a classical computer using some, let's say, like random number generator or something, or a density matrix formalism they call, a state vector formalism they call. So to understand how information get processed, these classical computers are very, very handy because the existing quantum computers are slightly noisy. Okay, so for that there is something called the quantum error correction is being used. That is, there is something called logical qubits people realize. Let's say they'll take 5 qubits, realize one logical qubit. Okay, so yeah, if people start using that, if then we can do the actual calculations. Which algorithm? Okay, any lab in India? Okay, that I answered. What are the current real-time applications of QML and which platform is the best suited for its development? Okay, existing QML real-time applications would be medical applications immediately. Okay, so finding, let's say, protein folding problem, if you find various ways of protein get folded, and then you will know the functions of the protein. So it is very, very difficult because protein is amino acid combination. Okay, so there are so many factors, so many parameters. So to process that lot of information, you need a memory. The classical memory is going to exhaust, so their quantum information or quantum memory is going to help. So that is the best choice for real world application. Okay, so there you can start with the VQE, QAOA optimization algorithms, which are part of quantum machine learning. People also started using neural networks, quantum neural networks. So there are layers, classical layers, quantum layers, and like that. So that is being picked up. Our conferences and journals allow these simulations. Yeah, you run something, some data, and then get some good result and show that it is novel, they will accept. Please repeat the name of the book. Okay. The name of the book I'll show you. Anyway, I am here. It is available on the net. Nielsen Chuang. Okay, it is available. PDF is available on the net. You can search PDF. Okay, this is the best book. You can download and you see how nicely it is describes. Okay, they start linear algebra is there somewhere. You can jump directly there. To second chapter you go, right? Finish. If somebody have no knowledge about quantum mechanics, use the second part of second chapter. Basically, you finish the second chapter. Okay. Then, if you want to study the from the bits, finish the second chapter, then come back to first chapter. Okay. So basically, everything is covered in the first chapter, the initial level, and then you go on to the advanced parts. Okay. So even the Turing machine is there, quantum computation is there, quantum circuits, quantum Fourier transform is there, search algorithms, Shor algorithm, all those things are there. Okay. Noise, quantum error correction is there. See here. So this book is nicely written, and there is a solution also available on the net. If you carefully check, you will get the solutions for the problems in the book. Okay, so I would suggest this is the best book as of now, but there are other books also available. I think it's up to you which one you choose, you find more comfortable. Okay, I'll stop and hand it over to the academy. Okay, let them take over. Yes, Shivan sir.
Great session, sir. Thank you for this particular session, and I hope the participants uh, understood it. And you can, if you have not, if you want to have a revision, you can see on YouTube also. So please go through it, and if you have any questions, you can email Ashwin sir. Yeah.
Yeah. Thank you.
Okay. I think we can stop the session.
Yeah, please carry on. Stop the
Yeah.
session.